Welcome to Demystifying Math. In this lesson, we're going to be finding the inverse of a 3 by 3 matrix. To find the inverse of a 3 by 3 matrix, we're going to augment it by using the 3 by 3 identity matrix. So that means that we're going to attach 3 rows where we have ones on the diagonals and zeros in all other positions. So now we have a 3 by 6 matrix. And what we're going to do is use row operations to find the inverse. In order to find the inverse, what we want to do is move the last 3 columns to become the first 3 columns. So our first 3 columns are going to be the identity matrix. Then when we're done, the last 3 columns will be the inverse of the matrix. So in order to make the first 3 columns have ones on the diagonals and zeros in all the other positions, we need to make the first entry in row 2 a 0. That's where we're going to start. And we're going to do that by taking our first row and multiplying it by 2 and adding it to row 2. Remember that when you are doing row operations, you can multiply any row by a non-zero constant, you can add any 2 rows together, and you can exchange rows. So let's go ahead and do this operation. We're going to multiply our first row by 2. So we have 2, negative 2, 4, 2, 0, and 0. Then we're going to add that to row 2. And the result is 0, 1, negative 1, 2, 1, and 0. Now that we're done with that, we're going to put that result into row 2. So we have a 0 in the first position of row 2. We also need a 0 in the first position of row 3. So now that I've rewritten my matrix, I can do row operations on the new rows. So I'm going to take row 1 and multiply it by negative 3 and add it to row 3. Then when I'm done, I'm going to put the result back into row 3. So multiplying the first row by negative 3, we have negative 3, 3, negative 6, negative 3, and 0, 0. Then we're adding that to row 3. So the result is 0, 5, negative 9, negative 3, and 0, 1. Now that's going to become our new row 3, so I'm going to write a new matrix. Okay, so the next thing that we want to do is to eliminate the 5 in row 3. We want that to be a 0 as well. So what we're going to do is take row 2 and multiply it by negative 5 and add it to row 3. So taking the row 2 and multiplying by negative 5, we have 0, negative 5, positive 5, negative 10, negative 5, and 0. Then we're going to add that to row 3, and we end up with 0, 0, negative 4, negative 13, negative 5, and 1. Now we want to put that back into row 3 because in row 3 we want the first 3 columns to be 0, 0, 1. So that gives us 2 zeros. Now we also need to have the first row to be a 0 in the second position. So we're going to add row 1 and row 2 together and put the result back into row 1. So adding them together we get 1, 0, 1, 3, 1, 0. And again, creating a new matrix by replacing row 1. And then what we're going to do is try to eliminate this 1 in column 3 on row 1. So we're going to take row 1 and multiply it by 4 and add it to row 3. And then we're going to put the result back into row 1. So multiplying our first row by 4, we have 4, 0, 4, 12, 4, 0. Adding that to row 3, we have 4, 0, 0, negative 1, negative 1, 1. Now when we put this back into row 1, you're probably thinking, well, we already had a 1 in position 1 of row 1. Why would we want to make it a 4? Well, as long as we're making some of the entries zeros, we can always divide the 4 out later on, which we will do. Okay, so here's our new matrix. In our next step, we're going to take row 2 and multiply it by -4 and add it to row 3. That's going to eliminate a position in column 3. And we're going to put that back into row 2 because that position needs to be a 0. So, taking row 2 and multiplying by -4, we have 0, -4, 4, -8, -4, 0. Adding that to row 3, we have 0, -4, 0, -21, -9, 1. So that's going to become our new row 2. So now what you should notice is that we have constants on the diagonal in the first 3 columns, and everything else is zeros. So from here it's easy to change those 4s, our -4s, into 1s. We're going to take our first row and divide by 4. Our second row we're going to divide by -3, and the same for the third row. And now here is our final matrix, where we have the identity matrix in the first 3 columns, and in the last 3 columns we have the inverse of the original matrix. Let's go ahead and verify that that is actually the inverse of the matrix that we started with. We can verify that by multiplying it by the original matrix. And when we multiply it, we should get the identity matrix. So what we're going to do is start multiplying rows by columns. So we're going to take our first row and multiply it by our first column. So remember that when you're doing matrix multiplication, the corresponding entries are multiplied and then added together. So what we're going to do is multiply 1 times -1/4 plus -1 times 21/4 plus 2 times 13/4. And then add those together and we got 1, which is what it should be. Now we're going to take row 1 and multiply it by column 2. So I have 1 times -1/4 plus -1 times 9/4 plus 2 times 5/4. And when we add those together we get 0, which we should get. So remember that if you're multiplying row 1 times column 2, the answer should go in row 1, column 2 of the resulting matrix. Now we're going to multiply row 1 times column 3. So we have 1 times 1/4 plus -1 times -1/4, which is positive 1/4. And 2 times -1/4 gives us -2/4. Notice I'm not putting my fractions in lowest terms because I knew that I would need a common denominator. Alright, so that comes out to 0, which is correct. Now that you've exhausted all the multiplications by row 1, move on to row 2 and multiply it by your first column, your second, and your third. So multiplying the second row by the first column, we have -2 times 1/4, which is positive 2/4. 3 times 21/4, which is 63/4. And -5 times 13/4, which gives us -65/4, which adds together to give us 0. Taking your second row and multiplying by your second column, you have -2 times -1/4, 3 times 9/4, and -5 times positive 5/4. And those add together to give us 1, which gives us the entry in row 2, column 2 on the resulting matrix. Now go ahead and finish that multiplication just to verify that you're getting what I'm getting here. And then you can see that yes, this is the identity matrix. So if you multiply a matrix by its inverse, you get the identity. It's kind of like taking a number like 3 and multiplying by its reciprocal. 3 times 1/3 is going to give you 1. And that's the concept that we're going to use to apply matrices to help us solve for a system of equations. So we're going to take this matrix and we want to rewrite it using, for instance, equations or expressions. So looking at our first row, it could represent x minus y plus 2z being the coefficients of x, y, and z. If we use the second row as the coefficients of x, y, and z, we get negative 2x plus 3y minus 5z. And the same for the third row. We end up with 3x plus 2y minus 3z. Now, if each one of those expressions were equal to a constant, we would have a system of equations. So in this case, we're going to let the first row equal negative 3, the second equation equal 10, and the third equal 15. Now, if we wanted to represent a system of equations with matrices, we would have a coefficient matrix times the xyz matrix equal to the constant matrix. Let's think about that for a minute. If you have a matrix multiplied by another matrix, you would do row times column. So our first row would be 1 times x plus negative 1 times y plus 2 times z, which gives us our first equation here equal to negative 3. Then your second row times xyz is going to give you the second equation that we had here, and the same for the third. So this is our matrix representation of a system of equations. Now, in order to solve for x, y, and z, we would divide by the matrix that it's multiplied by. When we divide by a matrix, it's the same as saying, well, the reciprocal of the matrix, or the inverse as we call it. So we've brought the matrix over to the other side of the equation and we're multiplying it by our constant matrix here. And we're isolating x, y, and z. Now remember that matrix multiplication is not commutative. So you have to kind of be careful and make sure that your inverse matrix is on the left, multiplied by the constant matrix on the right. Then it will always work for you. And in this case, we've already found the inverse of this matrix. So we're just going to change this to its inverse. So we have xyz is equal to the inverse in the matrix times the constant matrix. And we're going to multiply row by column. So multiplying our first row by the column, we have negative 1/4 times negative 3, which is 3/4, negative 1/4 times 10, which is negative 10/4, and positive 1/4 times 10, which is times 15, which is 15/4, which adds together to give us 8/4 or 2. Now we can do the same thing for the second row and the first column. So 21/4 times negative 3 is negative 63/4. 9/4 times 10 is 90/4. And negative 1/4 times 15 is negative 15/4. That's going to add together to give us 12/4 or 3. And you can verify the third column as well, which gives us negative 1. Which means that x, y, and z is equal to 2, 3, negative 1. So x is 2, y is 3, and z is negative 1, which is a solution to our system of equations. Now we can always check our work and make sure that we did it correctly. So going back to our system of equations, we're going to plug in 2 for x, 3 for y, and negative 1 for z, and check our work. So for the first equation, you have 2 minus 3 plus 2 times negative 1, which gives us negative 3. And you can verify it for the last two equations as well to see that you get 10 and 15. So this is your solution set. Okay, so thank you for tuning in to Demystifying Math.